Now we're going to look at double bonds in rings. And when you think about placing a double bond in a ring, the size of the ring really doesn't matter. So any ring can contain a double bond. We can start by looking at the smallest ring possible, a three-membered ring, and this is called cyclopropene. If you think about the alkane, it would be cyclopropane. So we're again dropping the ANE and adding an ENE. Now, cyclopropene is actually relatively unstable. If you think about the pi bond, the nature of the pi bond is from the overlap of two p orbitals. But in order for hybridization to be sp2 and have a p orbital available, the geometry has to be trigonal planar. And this isn't quite a trigonal planar geometry. And so that p orbital character actually has some s character in it. And so there is a weakening of that pi bond. Likewise with cyclobutene, right? We have kind of the same characteristics. And as we get into larger rings, we get more and more of that pi character back, to the point where if we're looking at a six-membered ring, now we can, the bond angles are certainly 120 degrees from one another. This is cyclohexene, and cyclohexene happens to be one of the most stable cycloalkenes that you can have. So that's with one bond. And of course, rings larger than cyclopropene can have more than one bond. So they can have two bonds, they can have three bonds. So we're talking about dienes or trienes. For example, a four-membered ring with two bonds is called cyclobutadiene. Cyclobutadiene. And of course, we can have a five-membered ring with two bonds, which is called cyclopentadiene. And now when you get into the larger rings, like a six-membered ring with two bonds, this is going to be cyclohexadiene. But now I have more than one way of orienting the two pi bonds. So I have to number the system 1, 2, 3, 4, 5, 6, and so you have to give a location for each pi bond. The first pi bond is on the 1 carbon, and then the second pi bond in this example is on the 4 carbon. Notice I could have put it on the 3 carbon. So in cyclohexadiene, I could have 1,3-cyclohexadiene, or in this particular case, I have 1,4-cyclohexadiene. Now, if you think about stereochemistry, we looked at alkenes and we saw that alkenes can have cis or trans stereoisomers, or EZ stereoisomers. With rings, the ring limits the rotation, and therefore, generally speaking, cycloalkenes are going to be more stable in the cis configuration. And it isn't until you get flexibility in the ring that you can accommodate a trans configuration. The largest, or I should say the smallest ring that can accommodate this is one that contains 8 carbons, which is cyclooctene. And therefore, cyclooctene and any larger ring is going to have the capacity to have 2 stereoisomers. So I'm going to draw here, in our typical ring fashion. This would be a cis configuration. So we would call this cis cyclooctene, or Z cyclooctene, Z cyclooctene. And of course you can have trans, or E cyclooctene. And the way that you show this is you basically have to kink that ring such that the two hydrogens are on opposite sides of one another, to provide that trans configuration. So this is called trans cyclooctene. Now it happens that even with as large a ring as 8 carbons, the trans configuration is still 11.5 kilocalories per mole less stable than the cis configuration. So what we're going to be dealing with most of the time is 6-membered rings or fewer, and therefore generally speaking, alkenes, cycloalkenes, are going to take on that cis configuration, and that's going to be assumed for the most part. Now, one thing that you can think about is taking two rings and putting them together. And when you take two or more rings and you put them together, there are two ways of doing that. There's a fused ring and there's a bridged ring. So when you have two rings that are that share two carbons here, this is what's called a fused ring. And the carbons that are shared between the two rings, or the carbons that are shared between any rings, are called bridgehead carbons. Bridgehead carbons. Now, it's important to understand, how many bridgeheads that you have when two rings are coming together. So when you have a fused ring, there's only the sharing of two carbons, and therefore there are only two bridgeheads. Okay? Now, if you think about a system like this, where in essence this is two rings that are fused together, and I have these three carbons that are being shared. In this situation, it's called a bridged bicyclic compound. So I have a fused bicyclic compound because there's two rings, or I can have a bridged bicyclic compound. And in a bridged bicyclic compound, it's sharing three carbons. Now, if we think about the geometry of bridged bicyclic compounds, cyclohexane, you can think about that cyclohexane ring, that bridged carbon actually puckers it a little bit. So we typically draw it like this, where the three shared carbons are right there. And that's something that, that we're going to have to get used to. Now, why do I bring this up now? Well, it was observed by a chemist named Julius Brett that in terms of cycloalkenes, there were no double bonds on any bridgehead of the bridged bicyclic compounds. So obviously you can, he saw, and there are plenty of examples of fused rings where there's a double bond at a bridgehead. But when you look at bicyclic compounds, there is no double bond at the bridgehead. So what do I mean by that? So here's an example of a scenario, a theoretical scenario, where I would have a double bond, and notice that double bond is at a bridgehead. And what Brett was saying is this can't happen. For some reason, these are not observed. Well, the question then is, why are they not observed? And again, we have to think about geometry. So if we think about geometry at that bridgehead, because we have a kind of puckered molecule, that carbon can't be planar. If it can't be planar, trigonal planar, right? So an sp2 carbon is trigonal planar. To have that p orbital, that means there's no true p orbital. And so two things actually come to play when we rationalize why we can't have a double bond at a bridgehead of a bridged bicyclic compound, right? We're trying to understand why the chemistry is the way it is, and that's very important to be able to do. So let's think about this. The first thing is obviously that bridgehead carbon isn't going to be have a true p orbital. There's going to be some s character in it. The second thing is, if we think about the overlap of the orbitals, if I look at the carbon on the right, it has, it can certainly be trigonal planar, and the p orbital would kind of be oriented in this fashion. Now, if I think about that bridgehead carbon, number one, it's going to have some s character, so it's not going to be a true p orbital. The other thing is its orientation. Now, I've tried to demonstrate the orientation by, that blue lobe coming out at me, right? That's a wedged orbital. And so, imagining the geometry, that geometry means that that orbital is almost perpendicular to the p orbital of the carbon on the left there. And therefore, the two orbitals can't align, and they therefore cannot create a pi bond. So it's important to understand why chemistry happens, not just to memorize facts, but to actually understand why things are happening. And this is very important as we go on, because the more that we can understand why things come together or they don't come together, then the more that we can predict reactions. And that's very important when we think about organic chemistry.